Tutorial 19. Timing Introduction. In this tutorial, we will be working with time objects that deal with time, and a set of objects that work with a metrical timing system built into Max. Additionally, we will look at some decision-making objects that use logic operations to determine program flow. As we've seen in earlier tutorials, the use of time is an important part of working with Max programs. Time-based objects like Metro can help create generative music and drawing actions, and can be used in conjunction with user actions to create playable programs. The transport objects in Max provide a centralized musical timing system that can provide play-stop controls, bar beat feedback, and can even cause events to fire at specific points in time. All of this is built on the ability to define specific times and time durations in metrically significant ways. In addition to the time functions, we also cover some of the Boolean comparison objects that create logical results based on comparing and testing input values. These are especially useful when working with time-based objects, since you will often want to make operational decisions based on comparisons between the current time and some desired time or subtime function. Some new objects. The left-hand side of the tutorial has 5 small patches that show the operation of a handful of new objects that deal with time in Max. Patch 1 provides an example of the pipe object, which can be used to delay the passage of any message or list for a certain amount of time. The argument provides the default delay time, in this case, 1000 milliseconds. If you change the value of the left number box, you will see your changes reflected in the output 1 second later. The delay time can be changed with a value sent to the right inlet. An integer value is used to set the number of milliseconds of delay time. Change the right-hand number box to 2000, then change the left input. You will now see the changes occur after a 2-second delay. The next small patch, labeled 2, is an example of the delay object. This is very similar to the pipe object, except that it is specifically tailored to delay bang messages. Like pipe, the delay time can be changed by sending an integer value into the right inlet. Both the delay and pipe objects will respond to a stop message to abort pending output. Patch 3 shows the clocker object, which is closely related to the metro object. The primary difference between clocker and metro is the output. While the metro object produces bang messages at regular intervals, clocker outputs the overall elapsed time since it was started with a bang. Clicking on the stop message will stop the clocker, while sending a new bang message to clocker will restart the timer and the elapsed time measurement. The patch labeled 4 demonstrates another object that counts elapsed time, the timer object. This object takes bang messages in both inlets. The left inlet starts the interval to be timed, and the right inlet stops the interval. The timer object is therefore equivalent to a stopwatch. Click the left-hand button to start the clock, wait a few seconds, and then click the right-hand button to see how much time has elapsed. Note that timer is a slightly unusual Max object in that its right inlet is hot, not its left inlet. The 5th patch shows some of the most common comparison objects in action. The object outputs a 1 if the incoming number is greater than the number used as an argument, or a 0 if it is not. The object therefore performs a test, reporting true or false. The object is the inverse, reporting true or false depending on whether the input is lower than the object's argument. The use of 1 or 0 to indicate true or false are in common use across programming languages, providing the foundation of Boolean operations. The remaining logical objects will probably be more familiar to programmers. The equals object reports a 1 only when the incoming number is equal to the argument, while the equals is its inverse. It reports a 1 when the incoming number is not equal to the argument. As with many Max objects, a new comparison operator can be supplied by a number sent into the right inlet of the object. The final 2 logical operators are AND and AND. In the first case, the AND object will output a 1 only if both numbers sent into the left and right inlets are non-zero, otherwise, it reports a 0. In the second case, the object will output a 1 when either the left or the right inlets are sent non-zero values. If both are 0, this object will output a 0. Change the number box at the top of the patch containing these objects, and you'll see how they behave. Notice how the only time all 6 operators yield a 1 is when the input value is 10. Metrical Timing, Part 1. The large patch on the right is a performance patch that uses all of these new objects within the context of the metrical timing system. Start the patch. You will hear a steady beat out of your default MIDI synthesizer, with variations that occur at different times throughout the performance. The performance is looped, rerunning itself every 16 measures. In order to understand this rather complex patch, we first need to understand the metrical time system. Metrical timing is based on a central timekeeping object, the transport, and its ability to broadcast time information to other objects that are expecting timing information. Many of these, listening, objects are already familiar to us or have been introduced in this tutorial. We have used these objects in self-clocking mode, where they use a time base expressed in milliseconds to produce output at regular times. When used in conjunction with the transport object, however, time is expressed using metrical notation. Values such as 4n can be used as an alternative to millisecond timing notation. The transport object is the central timekeeper, and provides time in bar beat tick format, all driven by a tempo and a time signature. Hence, if a transport is set to run with a time signature of 4/4 and at a tempo of 120 beats per minute, each beat will take 500 milliseconds, and a measure will take 2 seconds. In order to see all the ways the transport controls this patch, we need to break it down into sections. Our big checkbox starts the process mainly because it starts the transport. The transport accepts a 1-0 message for start and stop, which is perfect for control by a toggle. The toggle also starts the metro to the left, which uses 4n as the timing argument. In the past, we've used milliseconds for the metro object's timing, but in this case, the 4n notation means that it will send out a bang every quarter note, based on the timing broadcast by the transport. The output of this metro goes to two places: to a message box that creates a MIDI note 70, and back to the transport. Why does it get routed to the transport? Because a bang message received by the transport will cause it to output the current time, which we display in 3 number boxes connected to the first 3 outlets of the object. This time is displayed in bars, beats, and ticks, respectively. There are 480 ticks per beat. Next, let's look at the green section of the patch. This uses the bar count, and uses the and objects to determine if we are between bars 4 and 8. If we are in that range, it turns on another metro that is clocked at 16n. This generates a random number used to create one of 4 values. These numbers are sent to the MakeNote object to generate MIDI notes. That value is also sent to a pipe object with an argument of 4nd, which delays the values by a dotted quarter note. This output has 7 added to it, causing output that, when sent to the MIDI synthesizer, sounds a perfect fifth above the original. The result is a rapid-fire set of notes, for a 4-bar segment of the loop. Let's now dig into the blue section, which is the part of the patch that forces the sequence to loop. The head of this section of the patch is a new object, time point. The time point object takes a metrical time as an argument. Its sole purpose is to generate a bang message when that metrical time is reached by the transport. In this case, when we reach the beginning of the measure 17, a 4-note chord of numbers is sent to the MakeNote, then a bang message is sent all the way back to a message connected to the right inlet of the transport. This message tells the transport to immediately jump to tick 0 of the sequence, i.e. bar 1, beat 1 and tick 0. This is how we force the sequence to loop. Every time we hit the 17th bar, we are immediately sent back to the beginning. Metrical timing, part 2. Next, we should decode the brown section of the patch. It uses key and select objects to watch for the space bar being depressed. When this happens, a timer object receives a bang on both inlets. Because max objects transmit messages in right to left order, hitting the space bar simultaneously stops the timer with a bang to the right and restarts it for another measurement with a bang to the left. The object outputs the elapsed time in milliseconds. We divide 60,000 by the time to get a BPM value. However, we want this BPM value to fit in a sensible range, so we use the split object, and only use values that are between 30 and 200. If we are within this range, split will output the number from its left outlet, and the value gets used to create a tempo message that is sent to the transport. This will immediately change the playback tempo of the sequence, and will change the relative speeds of many of the objects used to create our sequence. If the timer outputs a value outside of the split object's range, it will be sent out the right outlet of the object and discarded. One of the reasons that not all of the sequence is changed is because some of the patch functions use standard timing rather than metrical time. The rightmost section of the patch is a good example. A time point object is fired when the transport time is at bar 6, beat 3. This starts a clocker that runs for 10 seconds, producing a 2-note chord every quarter note. The time point object also sends a bang to a delay 3000 object, which produces a 2-note chord 3000 milliseconds after it receives the message. At a very slow tempo, this may occur only a few beats after the time point is fired, while at rapid tempo, it may take many bars. This is a good example of how metrical and standard time can be mixed and matched for interesting generative results. Note that the clocker object's running time is compared against a object to switch itself off after 10 seconds. A timer object tracking the interval between the start and stop of the clocker object confirms this. The importance of overdrive. One factor that could cause variant behavior in this patch is the overdrive setting, found in the options menu. If overdrive is checked, event processing and calculations are given priority over screen drawing and graphical processes. When overdrive is unchecked, drawing processes get the same priority as event handling. Depending on the nature of your patch, overdrive may provide better performance for time-critical event handling tasks. Since our tutorial patch is, in fact, time-critical, it will perform best with overdrive turned on. If overdrive is off, you may see that the transport output display doesn't always occur on the 0 tick, and you may find that playback gets jerky when the density of notes is high or you perform other tasks on your computer. Modern computers are incredibly fast, but our ears are very sensitive to timing discontinuities. Therefore, when working on patches that sequence events in a time-critical way, it is normally advisable to turn overdrive on. Summary: in this tutorial, we covered an extensive new system within Max, the metrical timing system. This provides a centralized timing control for your Max patch, coordinating the generation of events and easing the creation of musical sequences. We also learned about several new time-based objects, including pipe, delay, clocker, and timer, which can be used to create sequenced actions. Finally, we saw the use of Boolean comparison and logical operator objects to aid in decision-making within a complex